My name is Jake Taylor. I'm at the National Institute of Standards and Technology and also at the Joint Quantum Institute and the Joint Center for Quantum Information and Computer Science. And the organizers asked me to speak about the broad-scale federal programs that already exist in quantum information science. And given the content we've had already this morning, I think there's some really interesting open questions about what the future opportunities are. So I won't get to a lot of those future opportunity details. I think that that's a really key question that is driven in part by the scientific dialogue that we're having in the room today. I have the benefit of speaking after a number of talks that were describing what the science is to help us illustrate the opportunity space and conversations about that opportunity space. I am providing you these slides because this is what I showed Congress. And so you have to get a sense of what your decision makers are thinking about, not just necessarily what the scientists are thinking about. And we often break up the different subfields of quantum information science into three key areas. The first of which, in some sense the most mature of which, is quantum sensing. And quantum sensing has two different modalities, one of which is accuracy via physical law. So you take a concept like atoms are indistinguishable, so an atom here and an atom there, if it's the same atom, I get the same results, and you can turn that into a clock. You take the concept that the speed of light is constant, and then you can turn a clock into a ruler. You take a concept like electrons have a quantized charge, you pump them by one, and that will create a current source. Each of these is actually how we now define physical constants and our measurements with the adoption of the SI, the readoption in 2019. So all of our measurements that you use when you're doing your Home Depot run through producing a probe to go to Mars, all use quantum units now. But the other approach, and this is an area where there's been a lot of applied math work, is in new modalities. So measuring in an area we just weren't able to measure before. And I think a number of you are familiar with the long and tremendous history in magnetic resonance imaging between physicists, chemists, engineers, and mathematicians to be able to do the thing of monitor the blood flow in your brain. That was a huge effort over many years, and that's the sort of thing that we're hoping to gestate from this conversation. A second key area is, of course, quantum computation, and this gets most of the oxygen in the room when you're surrounded by venture capitalists and or members of Congress. But I think it's worth being clear that the quantum computers we have today are in some fundamental sense toys that don't yet open up new fields of application outside of building a quantum computer. Now, they're very good at telling us how we might build a better quantum computer. And that's very exciting for a variety of reasons, actually. But I just want to be clear that we're still quite far away. One approach that people are using today in order to explore other areas of science using quantum machines is this area of quantum simulation. So this is without any error correction. And the best analogy that I provide is that of the Navier-Stokes equation, which is the equation of fluid dynamics. As you know, solving the Navier-Stokes equation is hard. In certain instances of it, you can show that it's NP hard. And what that means in practice is that we, as a society, build analog simulators like wind tunnels alongside supercomputing systems in order to build knowledge of what we actually want to build, in this case, say, a vehicle that has low air resistance. And quantum simulators provide the same basic benefit, but where the equation is the Schrodinger equation. And so you should think about what we're learning from quantum computers today as better ways for our human brains and the computing tools available to us classically to understand the quantum world. And then finally, there's quantum networking. This used to be called quantum communication back before quantum communication started being taken over by quantum key distribution. Quantum networking is the task of interconnecting qubits at distance. It has an application, quantum key distribution, but it has many other applications and has many beautiful results in complexity theory and applied mathematics, one of which I've highlighted here, which is the MIP star equals RE. These are transformative results about what is possible in the universe coming out of these ideas in networking. So I will mention these are the three main areas. The US government, of course, has an overall policy about this space. I say, of course, I had the pleasure of helping to write this back in 2018. This is the National Strategic Overview for Quantum Information Science. You can go to quantum.gov, download it if you want to read it. This is still the current strategy. And it has a few key components, the first of which is to take a science-first approach. So we wrote this policy in an era in which companies were getting started building large machines, and the responsible folks in the room said, none of those machines are going to be commercially viable in the next 3 years. What are you doing? And so as a society, we said, listen, we understand there's a lot of science to be done. Let us be clear that when we're asking for money, we're asking to do science. We're not going to sell you a machine next year. So that's the US government policy. And I think the speaker after me may come back to this question, because as we look at reauthorizing the National Quantum Initiative, which could happen this year or next, there's a question about, is it still a science problem? How much more engineering should we be doing? And I'll come to this also at the end of my discussion. But it's not just about doing science. It's about building the right and burgeoning and growing workforce. It's about figuring out how to build the partnerships with the groups that are now operating in industry and with groups operating in national laboratories, not just in academia. It's about producing the shared infrastructure that allows a small team to make a difference in a big project. And it's about making certain that we do this while we drive our economic growth, the underlying equation of work with us and we will jointly benefit in prosperity. This is how government policy translates into the actions around us, and the idea that we should collaborate together and work together is in part driven by the shared promise of future prosperity. But we have strategic competitors. So you have to do that with a balance with respect to how that impacts our future security. And then the US government policy is still to do a substantial international collaboration and cooperation where possible. This policy was translated into action back in the end of 2018 in the form of the National Quantum Initiative Act, which is an 11-year program that started then, and I've had the pleasure of leading it for the first several years, so I can talk about it in some detail if you have questions later. I think the key thing you should be aware is that this is a science initiative, not a technology initiative. This is really a huge expansion of effort in agencies that weren't doing quantum before, particularly the Department of Energy. And it's a civilian effort. You heard about Shor's algorithm and the interest of the defense communities. You know that precision navigation and timing is a key part of the defense sector, but the government effort is primarily a civilian effort. There's also coordination mechanisms so that the 13 federal agencies that provide funding in this space, not just the NSF, they're great, but also there's 12 others, don't step on each other's toes too much, make certain that performers who have something to bring to bear to a different program get a chance to talk to those other programs and so on. But in addition, we also worked hard in setting this up to really enable the innovation ecosystem. And this slide is very ugly. This was a pitch slide used inside the White House to pitch the National Quantum Initiative, so it's really ugly. It worked. About half of the effort, it's a $1 billion a year program, about half of the effort is in these sort of innovation ecosystem domains. And that's bringing different talent together into physical locales. So this shows up, practically speaking, in the form of these centers. The big Department of Energy centers, the big NSF centers, and also NIST has a few centers that we operate with universities. This is one of the big tent parts. Now, that's about half the budget, right? The other half, of course, is all of the small stuff, which is really, really important and requires everyone to work together. There's also, of course, a key part of how do you make certain that industry is at the table, that what industry learns, scientists can learn from, and vice versa. And to do that, we created the Quantum Economic Development Consortium, or the QEDC. This is created and led by NIST, but it is run by SRI International. It's primarily industry. It is where most industry gets together to ask questions of like, hey, do you need a new cryo system? I need a new cryo system. Hey, what about those microwave control systems? Hey, what about this error correcting code? Do we have decoders for that? And trying to identify the pieces industrially that are missing, that are shared pain points for the industry, and then develop those. And then there's the workforce. So this slide was made by the NIST team about what we want to do together. Prescient, you could say. We did this in 2017, this slide. Mathematicians, right there. Just going to call it out. Of course, I'll mention that again, which is actually applied math has been part of NIST's quantum program since we started in 1994. So from my perspective, it's of course natural, but I recognize that that's not the perspective of many of the academic world. And so it's interesting. And then, of course, there's this component of it, which is like not just the workforce that we're getting out of PhD programs, but all the way going down to middle school. How do we build this? And I think Emily Edwards may be speaking to this later. But where are we now? So, you know, when we first started thinking about doing initiative, it was actually all the way back in 2013. That was when Google purchased John Martinez's team. That was their computer on the left-hand side there. By 2021, the complexity has grown tremendously. And this engineering need is growing. I took a little detour from the federal government to work in the private sector for 18 months to help a company build a quantum error correction stack. By the way, the main algorithm that quantum computers run today is quantum error correction. Everything else is secondary. So if you're interested in algorithms and you really want to make an impact, that's where it is. But the point is that you can kind of identify that there's this really complex machine that you're building, and there's this huge stack of tooling in which it sits, and almost none of this is built. And so each of these has really interesting mathematical problems associated with it, some of which have been started to identify, many of which have not. And I just want to highlight that if all you did was all of this, we would all be gainfully employed for a very long time. The thing about error correction, and I mention it one last point here because I feel like this is really one of the most interesting areas, is that you have to improve your physical system performance because your qubits dephase and are noisy. And the way you do that is essentially you connect them together, you spread the information out into these diffusely entangled states so that if you measure any one qubit, you don't destroy the entanglement. And you then have to encode the information in these diffusely entangled states, process in these states, and then decode. And that is driven by tremendous advances in coding theory from the applied math and computer science communities. It's also driven by the practical implementation of these things. So this was the year that several teams went past break even in quantum error correction. They made logical qubits that had better performance than the physical qubits that they're built out of. It's been a pretty important year. Now, let's talk about, in the last little bit here, applied math. So NIST has had an applied math connection to quantum since we started our quantum program. We hosted the first workshop on quantum computing back in 1994. And that's when we started our quantum program. It's been a long time. 30 years later, we're looking back at it. I just threw up 3 examples of how applied math is sitting today in this infrastructure. So some of it is like our public service tools, like we have the quantum error correction zoo, the quantum algorithms zoo. That's one part. Another is we run a joint center. This is the Joint Center for Quantum Information and Computer Science. This is hosted at the University of Maryland. It has both pure and applied mathematicians, computer scientists, and physicists all sitting together. And then the third is we have a core quantum information program in our applied math division. And for those of you who aren't familiar with Manny Neal, of course, is one of the great giants of the field. He's been with us this entire way. And the reason we have this program, I want to be clear, the reason we have this program is because in 1995, we started building a quantum computer. So of course we needed our applied mathematicians to be helping us out. And so I want to highlight that if you ask what is the impetus to get your math program off the ground, it's really, if you're doing applied industrial math, it's because there's a problem. And it's finding who has the most interesting problem around and working on that. That's going to be the driver of successful grant proposals, the future of research, and the ability to actually create these complex, incredible machines. So I'm going to leave with this, which is the field of dreams. There's a lot that we'd like to do. Right now, what we're building is what's called small ball in baseball, which is we're trying to get the first runner on base. And where we'd like to get to are home runs, the scenarios in which we transform what's possible. And to bridge that gap is a huge challenge ahead. Thank you so much for your time. And I think we have a discussion afterwards, so we'll take questions then.